Hello everyone. First of all, let me thank you everyone for joining this session today. It's gonna be very exciting. Apologize for this little technical inconvenience, and this wants to be like a sort of follow-up of the discussion of the technical presentation made by Dr. Christoph Rojek about CFD suite earlier today. My name is Valerio Rizzo. I'm AI lead at Lenovo, and together with my panelists, we will discuss how AI can accelerate CFD, and we will wade into the subject from various perspectives. So I'm pleased to introduce you here with me, byteLAKE, Marcin Rojek and Mariusz Kolanko, co-founders of byteLAKE, company specialized in AI and HPC solution, building various products for different industry like manufacturing, hospitality, logistic, chemical, and one of these products is actually CFD suite, which is about to be discussed later. And then we have Dr. Damo Vedapuri and Ashish Kulkarni from Tridiagonal Solutions, which is a consulting house providing solution to process industry verticals like pharma, F&B, and chemicals. Dr. Damo Vedapuri is the co-founder and head, and Ashish Kulkarni is the head of delivery at Tridiagonal Solutions. Then we have a colleague for me, Robert Daigle, worldwide senior manager for artificial intelligence, innovation and business development at Lenovo. And Andrei Jankowski. I apologize if one of these names is misspelled, but Intel Corporation, Artificial Intelligence IoT at Intel, focusing on AI deployment. And I heard recently, and I read recently that he's also a part-time teacher, am I right, for hands-on lab AI stuff. So really exciting kind of panel. So I would like to start from a basic, probably an obvious question, but I bet some of the audience here is connected with CFD, more with the financial sector. I personally remember CFD being used increasingly in medical neuroscience for hemodynamic prediction related to intracranial aneurysm. But looking at the session description, I guess we are about to talk about chemistry, right? The chemical industry. So I would like to give a first help from Ashish here. Just introduce the topic, please. I know that you have a lot of experience in that, so who better than you can introduce us? And Ashish is no more there. Oh, is he?
Okay. So he's
no, I'm back.
Okay.
I'm back.
Thank you, Ashish.
Just in time.
Yes. All right. So Ashish, sure. If you want to introduce a little bit the topic, what is the CFD helping out us to understand better?
Correct. So let's say you ever wonder, if somebody near you sneezes, how far the spread will travel. Obviously, people may have seen some COVID simulations. If the guy is affected, how and where it's going to spread. Or if you are stuck in a New York traffic jam, what is the level of pollution you are getting exposed to? Okay, it could be as simple as we all love Pringles and the chips they produce. How come all of them taste so alike? And how come each of really the chip is equally tasty? Or what is the quickest way you fill in a shampoo bottle without getting foam and aeration and all those issues? Or unfortunately, we have so many wildfires in the California-Australia belt. What could be the best extinguishing strategies, or how do you decide for a given wind direction where the fire will spread? Guess what? Computational fluid dynamics really is going to help you to address these major concerns, right? And again, thanks to all these images, they are courtesy from a web search, but these are our real life scenarios and problems that CFD helps us to address and solve and provide really meaningful answers. However, there is one small problem, and that we will see if we go to the next slide. And the problem is, oh, damn, I have to solve this set of equations, correct? But if I can solve that, this is going to answer my first part and will take care of all my per se simulations. Unfortunately, these equations, they're popularly known as Navier-Stokes equations, but unfortunately, they are nonlinear, coupled, partial differential equations, a big dose of mathematics. Okay, and then there is no explicit equation for pressure. So most of the times you tend to use iterative methods. You need large matrices depending on how many nodes or how many cell points we are going to form this solution. And these procedures tend to be iterative. So you have to guess a solution and keep on improving your guess till kind of it meets a certain criteria, which we call as conservation. Whatever is coming in a particular system has to leave the system, or it has to kind of stay in the system. For example, heat getting received in the block at least has to increase the temperature of the block or leave the block, and that's the conservation. So these equations need to be solved, and that's what we tend to do with the help of computers, and that exactly is what CFD stands for. Okay, next slide, please. So CFD is nothing but a methodology of solving these equations, which are nothing but mass, momentum, energy, and other conservation equations with the help of numerical methods using computers. Okay, and that is how eventually it looks. You tend to solve it at each of those P's and W's and E's and whatnot, and that's how you constitute the whole suite of solution, and you keep on doing it in an iterative manner by solving matrices. Okay, and that is what really CFD stands for. Yeah, next slide, please. So this is a long journey. If you look at how far we have come in CFD, and again, this is a courtesy Wikipedia, that in 1910, that's how the activity started. Richardson actually hired 200 people and he paid them to retain numbers. Okay, he made them stand in blocks, and because the computers were not invented, and that is how the whole equation or simulation and iteration of those numbers came into existence. Okay, then there is a landmark paper by American article on CFD, followed by some other marker and cell methods and so on and so forth. But a major breakthrough, some attempts were also made by conventional finite difference, finite element methods. But I would say 1980 was a major breakthrough when people like Spalding and Pattankar from Imperial College really came up with this finite volume methods, which are much more aligned with the set of equations. And Pattankar also devised a method of resolving that challenge for pressure through his algorithm known as simple semi-implicit pressure-linked equations. Okay, that was a major landmark. Over a period of time, there are significant changes have happened. 2000, I would say there is a burst of commercial tools, and that's where the people like ANSYS and Siemens and others started getting popular. And 2004, I would say, is another landmark where open source alternative kind of disruptive technology under GPL licenses came into play. Okay, so Wikipedia covers it till 2004. What I feel has happened after that is in 2006, this whole polyhedra cell, cut cell philosophy, some merger and acquisitions also happened for companies, and they started becoming much more serious about this whole computational fluid dynamics as a science. Okay, 2010, I believe it was initially, if you see, this whole technology was much more dominated by aerospace just because lack of availability of data or huge monetary requirements to perform really experiments at a real scale. So over a period of time, besides aerospace and automotive industry, 2010-ish, the adoption increased substantially, and you will see oil and gas, process, food, pharmaceutical, all these industries started using technology. 2015 was the era when the buzzword was multiphysics. You are not just doing CFD or fluid dynamics anymore. It is getting coupled to look at, okay, what is the noise prediction? What is the disturbance because of pressure, and how does that translate to really create noise? Or coupling with a structure, saying, okay, what are the vibration issues? What are the failures of the structures? And so similarly, electromagnetic, magnetohydrodynamics. So along with the flow, many allied branches to solve really the actual set of problems. 2019, I believe automation was really the major focus. So a lot of automation of workflows, automated meshing, all those things came into play. Okay, 2020, anyway, nobody wants to know. It's a forgetful year. Okay, so let's leave that aside. And now we are in 2021. So historically, I would say these are the landmarks. And if you see how far we have reached today, it's everywhere. Okay, any problem you want to solve that involves knowing the flow, understanding it, okay, using it for certain modifications. Obviously, design of Formula One cars, all Boeing, or all these aircrafts made by fighter jets, okay, all of that. Large flows happening in oil and gas industry through a piping network, or even as simple our conventional problems as design of baby diapers or sanitary pads, the entire non-woven fiber structure. How do I decide which particular one has a better soaking capability, the capillary pressures requires and whatnot, or even the roasting of coffee beans and food grains. And guess what? The taste and aroma of that coffee is actually a strong function of how do you roast it. So roasting becomes equally critical because that controls the aroma and hence the cost of your coffee ingredient, the bean ingredient. The sewage water treatment plant and pump sumps, okay, all of us use laptops and so many electronic devices, and cooling is the only bottleneck there, okay. People are using heat sinks and other technologies which are coming up, but all those fans, doesn't matter whether it's actually a Lenovo computer or a Dell computer, effectively uses computational fluid dynamics for design of those fans. So technically, whenever you want to know the flow, you want to control the flow, you want to manipulate and adjust the flow, CFD is right there. Doesn't matter whether it's air, any other liquid, slurries, whatever is flowing, CFD is there. Yeah, next slide, please. So if you look at present approach, right, we have been doing it. Now I'm in this industry for last 20 years, right? Even in 2000, we used to play with 1 million cells. It was a big deal, okay? Probably 3 or 4 nodes getting connected. We are solving this big problem. Okay, there obviously the interconnects were not that developed and they were just coming up, I would say. But the computer power was limited and still we used to solve that problem. The geometry was limited. The physics was complex. We used to not capture all the ingredients and we used to solve it, okay? Moving back to today, in 2021 or 2020, what we say is the problem size has grown enormously. Okay, majority class of problems are like 5 million, 10 million cells. Even dealing with 50 to 100 million cells, solving not just airflow or external airflow, but even combustion, which involves multiple reactions and whatnot, is quite common. Okay, parallel to this, it has to do with how computers have evolved. Okay, and the newer processors have come up. The higher performance computing is made available. You have so many public and private cloud platforms that are available today. 500,000 nodes is easily available for any simulation across these compute powers. So everybody wants to do complex physics. That was always the case, but now with almost real life geometries. Okay, I don't want to make any simplifications. I want to capture the geometry as is and want to make an attempt in solving that problem. So the scenario had changed. Next slide, please. We have increased our compute power substantially to attempt larger and larger problem. So by and large, the hardware issue is resolved. From 4 nodes, we have come to 100 and 1,000 nodes. Okay, the processors are faster too. Software issue, commercial tools have been around. Okay, they were costly at that point. They are even costly today. Okay, yes, you have some open source alternatives, but at least you have an availability to make those solutions possible. Okay, unfortunately, what has not changed is our compute time. Okay, we used to solve these equations. It used to take 3-4 days to a week's time. That used to be the case earlier. That is still the case today. Even though I'm doing 1,000 nodes, I have to wait for a week. The customers are really in an aggressive mode. They are asking, okay, I don't want to wait for 4 days. Can I get the answer in 10 minutes? How do you take me there? Okay. And in that context, when we start looking at variety of things, we start questioning ourselves. Is the technology itself really catered to do that? Because we have been throwing so many nodes but started to attempt next and next level problems. Okay, so adding more capacity and compute power is never enough. Okay, so what do you do next? Do you want to do other methods like lattice Boltzmann, particle dynamics, and so on and so forth? They are coming up, but there are accuracy challenges there. So when we look at all of these, and in general, we are doing many more simulations, we thought, hey, will it be interesting if we use the past solutions and couple that with the actual artificial intelligence to predict the future? Okay, and that's what we started thinking, saying, how can I make it a game changer? How can I think it out of the box to reduce my simulation time from few days to actually few minutes? Okay, and how do I make it possible? And that's where we started searching over the web. We came across byteLAKE. They have a history of doing this AI. So we approached them and started joining hands to put together as an integration of CFD with AI.
Yeah, but
okay, so we started with CFD, and that's how we are now into the AI space.
Yeah, I guess it was easy to find byteLAKE. I mean, they are everywhere on the internet right now, thanks to this their new application. I mean, my feed is full of their stuff, so I bet it was like easy, very easy to find them. It's amazing what they are doing. They are receiving a lot of attention from either the media and the industry. And I would like to start hearing from Marcin and Mariusz about their solution and what how they came up with this CFD application for AI. Marcin, if you want to. Yep.
Yeah. So hello, thank you everyone for joining the session. We have now quite a crowded audience. So when it comes to byteLAKE, so we're not typical CFD company, if you like. We're more focused on the algorithmic side of the CFD, and so our aim is to adapt and to optimize different algorithms to various architectures, and nowadays to AI. I would say that our history in CFD starts like 10 years ago, when even before we branded ourselves as a team called byteLAKE, and then some of our engineers did their PhDs or DSCs along the way, and the first assignment or the first interaction with CFD was in the areas of weather predictions or generally climate simulations. So that at that time it was a challenge to, first of all, to move those complex algorithms that Ashish just outlined from typical desktop PCs to clusters. So it involved efforts related to optimizing software to many nodes, to CUDA from NVIDIA, to many Intel chips working together, and so on and so forth. And along the way, we experimented back in the days with machine learning. And in our case, it was mostly focused on dynamically steering the data types so that you can lower the compute amount and lower the data amount that needs to be transferred, so that eventually you end up having faster simulations. And the nice side effect along the way was always reduction on the energy consumption side as well. And I would say like that's how we started. So it started kind of naturally by analyzing the algorithms, and then Mariusz, you can tell our story with different platforms, right? Because that was also very exciting along the way.
Yeah, I hope that you can hear me. I had some problem with the microphone at the beginning, but
loud and clear.
Yeah, somebody forgot to add me my email to the panelists, so but now it's fixed. So hello to everyone once again. So as Marcin said, so in at that time it was really good experience for us to use machine learning for the CFD algorithm. So we experiment a lot with this porting our algorithms to the hardware, like GPUs from NVIDIA or Alveo FPGA card. We also did some research in that space using distributed computing, like MPIs or many nodes of these GPUs or FPGA, but still something wasn't enough. Even if this acceleration were promising with some cases or some simulation, as you heard Ashish, there was still some space or some room for optimization. So this is what we did. So we started to think how to go further with this, all those experiments, and we thought about why not to use AI and why not to use deep learning to accelerate it even more and deliver the new value for the CFD world.
Okay, got it. So let me understand a little bit better. Are you like a CFD company doing AI or the other way around? Because now I'm getting a little bit confused here.
And that's normal, Valerio. So don't worry. So we get this question that's very natural. So I will simply say that we're 100% AI company, but AI domain is so different from what we've been dealing with maybe in the past in the IT sector, is that it goes across various domains. So we as a AI company, we very much leverage the expertise of our partners, and that's why we are very happy to collaborate with guys from Tridiagonal Solutions, with Lenovo, of course, and with Intel here. As when it comes to CFD specifically, it's not just about being an AI company. You need to know how to manage the data, how to optimize the data. You need to basically know a little bit of the data science, know a lot about math. So you need to be really strong in mathematical solutions, equations, and so on. You need to understand the physics, but you also need to have domain experts. And team like Tridiagonal Solutions, they've been working in the CFD space for many years. And then all of this experience is very important to prepare the simulations, to prepare the data for training and so on. And as Ashish said, people do CFD anyway, so there's a lot of data that we can leverage or we can build on our solution. And then so our solution, as you can see on the screen, is completely data-driven at this stage, meaning that we take past simulations, we leverage this to find some patterns and build predictions on top of it with machine learning or with deep learning. And with that, we try to predict the outcome of the simulation so that we can eventually accelerate time to results, right? Mm-hmm. And then, as you can see on the screen, our aim is also to have this solution pretty straightforward in terms of integration, so that it's more like an add-on, right? We know that CFD people are very used to their existing workflows, existing tool chains, and so on, and we don't want to destroy that. So it's not like the revolution, right? So answering your question about, I'll bit extended it to our take on CFD in general. We're an AI company, but we very much collaborate with partners that have this domain expertise. And I think there needs to be a match. Like we need to have both, right? Yeah. So it's very much team going across many domains.
I mean, and something that we see nowadays is that AI or deep learning approach, I mean, to be more precise, are having a huge impact in different verticals, right? Like different use case application from computer vision, sound analysis, natural language processing, and now like we see like this new advancement in computational fluid dynamics, and so I've seen that it's having like a lot of impact in overall in the manufacturing industry. I would like to hear from Andrei, which is a veteran in this sense, like working with IoT, sensoristic, and now with AI application into business. What is his take on this? How the business changed across the time? So if you can give us some.
Yeah, no, sure. So I tell you, AI, it looks like AI is coming everywhere pretty much. And well, I believe that it's very helpful to have a kind of framework to understand why is this and what we can expect in the future. So from this perspective, I'm not too surprised that AI is used for CFD. There is a fantastic book. It's called Prediction Machines. It's written by two economists from Canada that focus on AI, but they are just economists at the end. And they talk about the way that economists are looking at the market and looking at new technology at the same time. So basically, as you know, in economy, it's all about price, and it's all about a market, market demand, I would say like this. And they say that actually price changes a lot of things. So if something gets cheaper, you basically use more of it. Yeah, and they give an example of computers. So when computers or calculation got cheaper, yeah, we started using more of it. Yeah, people started buying computers. So that's on one hand, but the other thing that happens also very often, and this is actually very similar to what happens with CFD, and that the topic that we talked today, also because some stuff is cheaper, people try to use it in a domain outside of the domain that it was designed for. And if you look at computers and where it happens, but the best example that they give in a book, it's actually photography. So photography was a domain of chemistry before computers, started being much cheaper. So actually, if you wanted to take a photo, you took a camera, you took a film, and then you have to go to, well, pretty much a chemist. It was called a photographer, but it was using chemical reactions to get you this photograph. But then when you got the computers and calculation cheaper, actually people turn photography into calculation. Yeah, so well, you had to you just shoot a photo with your phone. You don't have to develop it using any chemical reactions. And when I look at CFD, I think the same thing. Yeah, so what AI gives us? AI gives us access to much cheaper predictions. Yeah, so right now it's actually quite cheap to predict something. Yeah, and also with great accuracy, yeah, which Krzysztof were talking about at his presentation. So the thing is, you have now people have a relatively fast and cheap method to predict something. So instead of doing step-by-step calculation in this big CFD process, they can predict how the system state would look like, across many steps, and make it much faster. So I think using this kind of framework, it's a good way to understand where AI is applicable and why it's applicable to a domains which you may not think it would be useful for.
Yeah, totally agree. So something that pops in my mind. Tridiagonal and Ashish said, told about their story on how they found out about byteLAKE research and development, and it was, kind of funny for me, because I thought, okay, if I was a businessman and I had to find the solution for something, should I Google online? Should I? What is the right path to find the solution for my problem? That can be really challenging, right? Like the landscape can be really a maze, and right now, like all the technological stack and all those various ISV that you have in the market are really you have myriad of them. So Robert, what is your angle on that? How, can you say something about how would be the best approach to find somebody like byteLAKE, and how Lenovo is helping in that field?
Sure. Yeah. So there's a lot of different ways that we're seeing AI being leveraged in traditional areas of research like CFD. But many different workflows and use cases across research and across enterprises. That's something that we've really seen a change over the past, I would say, 18 months to 2 years, where we're seeing more and more AI projects come to life and moving out of that, research and experimentation phase, moving out of the POC phase and moving into real deployments, enterprise deployments. So that's been really exciting to see. And how we help customers at Lenovo through that journey is we start with a strong partner ecosystem with really great partners like Intel, like Tridiagonal Solutions, like byteLAKE. We've done a lot of great work with byteLAKE over the past 18 months. They've been a great partner for us. But we actually get started in our Lenovo AI Innovation Centers. So we have dedicated sites around the world where we have data scientists, AI architects, engineers, equipment, and really all of the solutions that we can bring to a customer to help them get started. So whatever they're trying to tackle, we start in the AI Innovation Center and look at how we can apply AI to their organizational challenge.
I see, like really interesting. So I know a little bit about that. I mean, we work in the same company. So I know all the good stuff we do, and it's and I would say like it's amazing, and also be surrounded by all these bright people such as byteLAKE. It's and see them working and solving problem. It's something that is really mind blowing. So I want to go a little bit deeper now in the topic. I would like you guys, Marcin, Mariusz, to tell us something about more, because I see already people starting asking questions about how the technology works, what is the benefit, and all the rest. So please give us some more insight about your solution.
Absolutely. And so first of all, like a little bit background. So what we're simulating here, and I will go down into the details. So we're simulating here a phenomenon which is related to chemical mixing, and based on CFD simulations, we predict with AI different parameters like velocity, pressure, some kinetic energy or turbulent parameters as well. And so our approach, as you could see on the previous slide, is very much data driven. And data in that context is not a problem, because people do simulations as anyway. But so looking into AI that we're using, it's a simplified ResNet, so that we can handle pretty significant amount of data. And currently what we're working with is are the simulations that take around 1 million cells as an input. So it's pretty huge. And then we work with 3D data. So every input we're sending to the simulation is in 3D format. And we also get returns and results in 3D input data. And when you look at the architecture, it looks this way, that on the training side, we need to prepare tens of different simulations, and in our case, it's roughly around 40 simulations. So you can judge it yourself if it's too much or if it's big or not. In general, it's not, and you just run those simulations. We take those simulations data for the training, which lasts in our case a couple of days, running on 2 NVIDIA V100 device cards. But on the inferencing side, what we're doing, we collaborate with again with traditional CFD solvers. That's why I said earlier that we don't introduce a revolution to the CFD people. We introduce an add-on which can be integrated in a quite straightforward manner. So what it does, what you can see here on the screen, is that let's imagine a typical simulation that needs roughly around 5,000 iterations in a steady state format, so that it converges until a final state. And then what we do, we run a fraction of that simulation initially to fuel the AI model, and in that case we run every 20th. We need every 20th step of the iteration, like first, let's say 480 iterations, and then from that point on, AI takes over and runs the prediction and gives the results almost immediately. and we call that submodels. And by saying so, we created different models per each parameter. So we can imagine that CFD simulation is not as straightforward simulation that you just get one answer at the end, but you need to predict a number of parameters. For most of these parameters, we have separate models which run in parallel, and each takes some fraction of the initial simulation. And based on that, immediately you move to the final results. And the very important thing here is that we're dealing with huge amount of data, right? Million cells. We're dealing with each cell being described in 3D points, and within a fraction of the second after preparing the initial data, you get the results. That overall, that gives us the acceleration at the level of at least 10x. And I will show you the accuracy that we're getting, and that will Mariusz guide you through.
Yeah.
So this is exactly. So currently we are focusing on the steady state simulations. The simulations are the kind that they stays in a state that the simulation ended. So this is how we are dealing it currently. So as you can see on the screen, this is the screen for from the Mixit from our partner Tridiagonal Solutions. And by the way, it's a great tool. Thank you guys for that. So you can see we are talking about the 3 types of simulation. We develop fast, medium, and accuracy one. So depending what you would like to achieve, are you going to focus on accuracy, or maybe time to result is most important for you? So depending on that, we prepared 3 types of the simulations. And on the screen, you can see that there is some kind of a liquid in tank with the propeller in the middle. And on the left-hand side, you are seeing the results from the real-life CFD simulation. And on the right-hand side, you can see the CFD suite results. So something that we did using our tool, CFD suite from byteLAKE. So as you can see on the first glance, difference are almost not visible. So there's almost the same results what we can get from the CFD, but much more faster result we can get from there. And actually the simulation and the prediction is roughly around 1% of that. So there's a lot of situations that we would like to have and the simulation much more faster with the accuracy, with the error no more than 1%. So it's really huge results that we can offer here.
And here the deviation is roughly around 1.5%. And as you could hear earlier in the discussion, the goal was to work on a solution that would help us go with the speed up beyond what's possible by just adding more cores or adding GPUs or what have you into your cluster, right? With that in mind, here we're talking about accelerating the simulations all the way from hours to minutes, or reducing the simulation iterations of several thousand to maybe couple of hundreds or maybe even tens of simulations, right?
I see. So and that is fantastic, but and you mentioned something. Your aim was not to completely revolutionize the CFD field, but rather like being an add-on to that field. So is it going to be available for existing CFD user? I mean, how to integrate the AI solver into pre-existing the CFD pipeline and tool chain? Ashish, what is your experience on that?
Sure, Valerio. So is over. I think we are in a phase where we are testing the whole operating range and verifying that the level that post-trial cases, our first task, and then we tend to offer it in a fully So the beta will be made available in next few weeks for internal release, and I think we will go in a fully integrated manner in few months from now. And at the same time, we'll highlight the accuracy level. And typically in AI, the more cases you have, this whole training becomes substantial, and the level of accuracy keep on increasing. So there is only upward to look at. As you do more and more number crunching, the level of accuracy you are going to get is going to increase substantially. That's the vision, and that's the plan we have for now.
I will add that regarding this, what I said, that we don't want to revolutionize the CFD field. I mean, from the workflow point of view, because what we see, we don't want to change people's habits in terms of which tools they're using or how the workflow is created on their side, but AI for CFD in general, this is quite a change, I can tell you guys. It's not just that we created this technology, but looking at the research space and looking at the overall efforts related to that, and the early results that we're seeing, like you can see on the screen, that is going to be quite a big change, leading you to running more simulations within the same budgets, reducing the cost of trial and errors, perhaps in the future even running more complex simulations. So that's a new way of things that we can do with CFD, and I think technologies like that will help us also understand more what we can do.
Valerio, we cannot hear you.
Yeah, so I was saying, yeah, that is a very good point. Also, because one of the major struggle when a new technology comes into place is the fact that you have to adapt everything to the like change completely the workflow, or going through the new learning curve, or you know, adapt your work to this new tool. Instead, if you can actually plug into pre-existing tools and making like basically the integration almost invisible and working on the background while you do the same work you have always done, but speeding up the process, that is I guess like that is a massive changes and a massive revolution conceptually. So, and I would like to ask Damo, so what is the typical application you've been working together with byteLAKE? I can see some tanks there, so it's on the chart. So can you make me understand a little bit better, and can you make understand also our audience?
Sure. Thank you, Valerio. Can I have my slides there? That may be a little bit easier.
Absolutely. Yep.
Yeah, fair enough, right? So just you know, appreciate the opportunity here. Good afternoon to everyone. I recognize that there's a lot of people out there that could be coming from other industries that may be curious about this application. And I just wanted to take a minute and let you know, just elaborate that the world of mixing is all around us, right? So you could be, you know, you get up in the morning, you use your toothpaste, you move on, take a shower, your shampoos, and all the facial creams that you may use, et cetera, right? So what you see up there is, you know, shampoos and creams and tonic and pasta sauce and paint and pigments. See, all of these products are all around us, and all of these products are typically made in a stirred tank, right? So this is a tank, and inside the tank, you typically have like a propeller that's moving things, right? So everything starts in a lab where beautiful recipes are created, and you're typically making them in, you know, practically pots and pans, right, in your lab, right? So that's what's happening. But once you have this beautiful recipe and you want to really take it to the market, you're going to want to know how to make these in really large tanks, right? So in large quantities. And one of the key elements in there as well, it's like, cooking a meal for 2 or 3 people, right? So you have a lot of control on your flavors. But imagine trying to make food for a party of 1,000 people, right? So all of a sudden you're going to realize that the flavor isn't exactly how it would be, and whatnot, right? So the quality, one of the key aspects is the quality of the mixing, right? So the quality of the mixing kind of controls the quality of the product. And so we've been working on this application for a while. Can I have the next slide, Mario?
I guess Marcin has control on that. Yeah.
Okay. Yeah. So basically, what you see here is, essentially on the left side, it's just a quick schematic to tell you that you've got a tank. The tank will typically have a propeller, some kind of an impeller system that lets you move these liquids around. And you've got a lot of things going on inside these tanks, right? So you could be mixing stuff, you could be heating them, you could be cooling them, and you could be having some reactions in there, and you could have powders, salts, sugar that are all dissolving and disappearing and mixing up with the liquid. So there's so much going on in these tanks, right? So now when you look at it, right, on the right side, I've just given you a certain, range of how these tanks look like, right? So as you can see there, no tank looks similar. They're all over the place, right? So the question is, you've got these interesting recipes that you've built in your lab, and you've got all these different tanks possibly in your plant. How do you kind of learn how to make the product in these large tanks, right? So that is where we utilize the CFD technology. And can we go to the next slide? Yeah. So what we've done here is, we've put together a product here called Mixit. And Mixit's a product that is designed to allow a traditional chemical engineer, a chemist, a biologist, understand what type of mixing you could experience in a particular tank, right? So we recognize your tanks are all different, and Mixit will allow you to understand the quality of mixing that you will get in each of these tanks for different recipes that you may be sending down these tanks, right? So it's a pretty unique tool. It's fairly automated, and it relies on CFD as a technology. And that requires a lot of steps. When I started in this industry about 20 years ago, it would take us about a few weeks to run a simulation and understand what goes on in a tank. Today, I would say we're down into the hours, maybe a day or so, and not in the order of weeks. And so Mixit's a tool that's enabling a lot of these engineers to run through these CFD analysis in a fairly automated way, and speeds up a lot of the engineering time associated with that. Next slide. Yes. So when what you see here is basically looking at what I was talking before is the so-called quality of mixing in a tank that are generated by Mixit. So when you use a tool like Mixit, you're able to understand the quality of mixing. And what you see there on the top are basically what we call as contour maps on the top left corner. And blue basically indicates a region where you've got very poor mixing, and red indicates regions where you've got a lot of velocity and a lot of mixing happening, right? So basically what we see there is, you can compare tanks, you can understand how, as you change the tank types and so on, what happens to these tanks, right? And on the bottom left, what you see there is what's called velocity vector plots. And these kind of show you the velocities and the direction of these velocities and the way the mixing is going on in the tank. And on the right side, you're looking at a tank in which we're trying to throw some solids in. We're trying to suspend the solids. We're trying to change the impeller rotation speed. And as you change the rotation speed, we're trying to understand, what's happening to the solids. and what's happening to the velocity contours, right? So typically in a traditional mixing analysis, we kind of want to know the quality of mixing, right? Do I have these regions where there's no mixing happening, the so-called blue spots? And where do I have my red spots? Where do I have my green spots? And I want to understand when I throw these particles in, are the particles moving? Are they just sitting at the bottom? Are they just sitting on the top? So the CFD as a framework and Mixit as a tool allows people to very quickly visualize these things. And when I say quickly, again, we're still talking of, you know, the order of hours here, right? And moving to the next slide, Marcin. Yeah. So typically today, you could take anywhere from about 8 to 10 hours to complete some of these simulations. More hardware gets you a little bit lesser time. But, you know, process engineers and scientists are all looking to do what we call as a design sweep, right? So they have this large matrix of conditions that they want to quickly run through and understand what's going on. So they are looking for, hey, can we get these simulations down to about 10 to 15 minutes, right? So what you need to recognize is throwing more hardware at it does not yield an answer to that problem beyond a point, right? There is a scalability limit in throwing hardware, which means you need to have an alternate way of speeding things up. And that is where we were looking around and we came across byteLAKE and you know, they were promoting their AI for CFD suite. And we said, hey, you know, that would be an interesting way to look at this problem is, you know, we have, you know, sped things up on the hardware side. Now it's time to look at other ways to speed things up. And if we can get things down in 10 to 15 minute range, then it allows these scientists and engineers to go through a large design sweep fairly quickly, right? So that is what prompted us to look into it. And then the question then comes in is essentially, can we build a universal AI model that works for all tanks across the world in all different configurations? Or should we break them into families of geometries and look at how they work, right? So these are all some of the current work in progress that we have going on. But overall, we're very excited to be introducing AI in the world of mixing to help engineers and scientists to speed things up and solve problems. Thank you.
All right. Thank you, Damo. And based on what you said, like it sounds like this is a kind of this is like a kind of 3D problem. So we are dealing with 3D data, and I can see the simulation living in a 3D world. So on the other side, I've seen some of the frameworks are there used by for deep learning, adopting coming out with new updates and release, such as PyTorch 3D, for example, TensorFlow 3D. So my question to byteLAKE is, so AI can actually, deep learning can actually predict 3D result?
Yes, that is correct. That's correct, and I would say that all these challenges that Damo outlined are very much valid. And as you could see in those tanks, all of the data basically that we get as an input comes as in a 3D format. So that's where we started, and the network is designed by default to work with 3D.
I see. So yeah, this is something that I was curious about. Like you described this process, like I've seen articles, blogs, and groups, and I remember, because this is something that we had some work together on FPGA's acceleration. You attempted to speed up this kind of computation on GPUs. And so what was the roadblock with other technology, and where AI actually makes a difference?
Yeah, so I can start with that again. So basically, during the course of the past years, we tried different approaches with CFD, and going back to the times where we dealt with climate simulations, our first attempt to optimize the CFD calculations was to move them back in the days from Fortran to C++, then to move it to many nodes configurations, so basically having many computers connected to each other, and then to platforms that can have either many GPUs or even many CPUs, so MPI and so on. And all of this led us to always significant effort. And then we tried with some simplified models like advection, for instance, which is a part of larger solvers. And we ported and adapted them to different platforms like GPUs or Alveo FPGAs from Xilinx. And then with every such approach, the roadblock was that, first of all, it takes time. So in our case, the effort to optimize the whole solver for a platform was counted like around a year or even 2. And then the acceleration that we got was in the range of 2 to 4x. So we, and also at the same time, in parallel, we experimented with different types of machine learning along the way, and eventually decided that, yeah, this gives promising results in many aspects. Like you can play with data types, you can predict certain things, you can skip iterations, or you can interact with the solver so that you get leap over certain amount of iterations, or you go directly to the final one. And with that in mind, we decided to move completely 100% toward deep learning. And currently, the effort is that training is done naturally on NVIDIA. We're using 2 V100s, but there is also an effort in the background to see how training can behave in Intel-only architectures. And the inferencing is on Intel. And the interesting thing is that the models for CFD are so complex that when we benchmarked the inferencing side on CPU only versus GPU only, the CPU only turned out to be up to 7 times faster. And that is even before we go to any optimizations like, OpenVINO or, and I think Andrzej will talk more about this still. But yeah, so that's the approach. And in a way, we can say that we're cross-platform because we work with TensorFlow as well. So that's available across platform. But it happens that CFD world is currently mostly on CPU only, right? And then training needs to be done currently on GPUs. So that's where we are, and that's how we overcome those roadblocks.
Yeah, and actually there was one question in our chat that was referring some kind to that. There was the question from Patrick, and what was some most challenging aspect to prepare such solution that we did. So the answer is that there's a lot of competences that we had to have in place. It was AI, machine learning, physics, computer science, CFD. So some of them we have on board already, but to others, we need to cooperate with such partners like Tridiagonal, Lenovo, or Intel. So the whole strength here is that we were able to work together to have this solution ready.
Yeah, fully understand. And so, Andrei, I would like to hear you on this point. Like, if you can give us also your angle on that.
Yeah, so yes, as Marcin said, part of the problem was actually technical one on the inference side, because when you look at the AI world right now, majority of the effort is in building, state-of-the-art models, so really training. But the majority of the kind of business value is generating on deploying the model. Yeah, and this is I believe where Intel can help. So I started working with byteLAKE actually on slightly different project, because we started working on byteLAKE solution for monitoring manufacturing process, where they were deploying edge devices to do the inference at the edge, and actually where customer wanted some solution that it's a bit cheaper. I mean, doesn't have to use an accelerators, and second thing that it's easier to maintain again. So if you talk about end customers, they don't like that much having some exotic architecture being deployed, yeah, because they need to learn how to install, the drivers, update it, and stuff like that. So when we started working, actually the byteLAKE solution was on accelerator, but then going through the stages of using Intel AI software, we have quite a few software offerings that enable you to make your models more efficient, yeah, and using OpenVINO, they got actually the industrial solution to work 10 times faster than the same solution using accelerator. So for them, it was a big win, not because of the software, yeah, but because this is much more attractive proposition for end user. As I said, end users already have PCs, yeah, so they have edge devices.
They can leverage what they have. Yeah, absolutely.
So I will quickly add that we want to revolutionize CFD in a way that you can do more faster and tackle on bigger problems, but at the same time, we don't want to enforce the industry to change everything, like workflow, hardware, what have you, right? It just needs to be straightforward. As we discussed earlier, there will be a button, just run faster.
Yeah, that's fine. That would be. I mean, this is when I hear something like that, I always think about like Einstein once said, "When the answer is simple, God is speaking to you." So making stuff simple is something that should be the aim. But I mean, I hear here like GPUs for training, CPUs for inference. So like we are bringing here a lot of different technological stack and components, and that leads, I guess, to some effort. It has to lead to some effort to make everything more scalable, simple, and to orchestrate this job in a more efficient way. I would like to hear from Robert what Lenovo is doing to make things simple, actually, like and to optimize the utilization of resources that otherwise could be really expensive.
When you're talking about CFD or AI, simple is relative. So keep that in mind. But we are trying to make it easier for organizations to adopt HPC workloads, whether it's an enterprise organization that's bringing in CFD workloads into their environment, or if they're looking to infuse AI into an existing workflow. One of the things that comes up over and over again is whether or not organizations want to buy new infrastructure or make use of existing infrastructure, and especially when you get into using accelerators that are quite expensive for training some of these deep learning models. How do you make the most use of that hardware? And what we've come up with is something that we call Lenovo Intelligent Computing Orchestration, which is a long word or sentence, but we call it LECO for short. And it's a orchestration platform for both HPC and AI workloads that you can manage both users, both workload types, all of your common frameworks like TensorFlow and Caffe. You can use pre-trained models and also fully optimized containers that are already optimized for your workload, whether it's an AI workload or HPC workload. So it's really a robust platform for both the HPC side of the house and the AI side of the house, where you can manage both users in a single environment, or users that, in this situation, may be doing both CFD and AI in a single workflow. So that's something we've been working with Intel on as well, to optimize our platform to take advantage of Intel CPUs as well, both the training and inferencing.
All right. So, okay, time. I mean, Teresa is asking for the audience to grab a coffee, so I guess it's time to wrap up and open the Q&A session. I think we heard here a nice story. I mean, we heard around like since the AI started to be like hype, everything related to the convergence of HPC and AI. And in this case, we are not just seeing like this as an under an infrastructural standpoint, but also in terms of use case application and intersection of application. And I guess it's amazing what byteLAKE is doing and how it's able to accelerate using AI CFD beyond 10x. With that said, I want to thank all the panelists here. It was really a nice discussion, a lot of food for the brain, and I will open the Q&A session. If you want to ask something more and going deeper into this discussion, feel free to write in the chat or on Slido. So thank you all.
Thanks a lot.
Thank you very much.
Thank you, guys.
And I entered in the chat. I entered our email to the team, which is cfdsuite@bytelake.com. And if you end up having any follow-up questions, also later on, just feel free to reach out to us, and we will simply include the whole team, Tridiagonal Solutions, Intel, and Lenovo into providing the comprehensive answer.
Thank you, everyone.
Thanks.
Thank you very much.
We are at the end. Thank you.
Thank you.
Thank
Bye.
you
very much. Have a great day.
Have a great weekend.
Enjoy your coffee. Have a
Bye.
great weekend.
Thanks, everyone.
Thank you very much.
Take care.
Thanks. Take care.